Okay. So welcome everybody. Today we have Aurelia Chenu from the University of Luxembourg. And please, can you mute yourself, everybody? Or go on mute, please, because we are starting. Okay. And as you can see, she will be talking about non-Hermitian Hamiltonians to handle particle lifetimes in coupled quantum wells. So whenever you're ready, go ahead, Aurelia.
Thank you. Thank you very much as well for the introduction, for this opportunity to present this work. So I put it in two parts, like a non-Hermitian Hamiltonian first in coupled quantum well, and then in open dynamics. And we'll see according to the time for these two parts. So I recently joined the University of Luxembourg, where I'm building my group. Federico in the audience will actually be joining us soon. So we are currently situated in the center of Luxembourg City, but they are building a brand new campus from an old industrial site at the border with France. So this is in Belval, and let's see how it goes. So the talk is on non-Hermitian Hamiltonian first, to get the spectra of polaritons and dipolaritons in coupled quantum wells. And in the second part, that would be shorter, it's on the use of non-Hermitian Hamiltonian to do a scheme to control and hopefully fasten the dynamics of open quantum system. So let me start with the first part that has been done in collaboration with Sean Xiao, Poki Xian, and Monique Combesco. And before giving the motivation, I'll just briefly introduce this coupled quantum well, which is a very nice platform to study the quantum properties of excitons. So in these wells, we can do direct excitons. That would be a superposition of an electron and a whole wave function. And this is direct because the two of them are in the same well. Now, if there is a field applied on the structure, so here you can see this is in space set, and this is in energy. So if there's a field applied, one can create as well these indirect excitons where the electron and the hole are in two different wells. So the advantage of this is that there is a built-in electric dipole moment that can be controlled by the electric field that one applies on the structure. And as well, since there is a very small overlap between the electron and hole, this reduces the radiative recombinations, which means that the lifetime of such indirect excitons is long. It's orders of magnitude longer than the direct excitons and can be up to 10 nanoseconds or 10 microseconds. So one can have this nice long coherence time. Some application of this structure, thanks to these particularities and the controllable dipole moment, is to create create long-lived quantum states and control exciton transport from electrostatic or optical properties. So here we see the photoluminescence signal of some indirect exciton that has been observed in a quantum well. One can as well do electronic devices, for example, a diode a transistor. This would be an optically controlled excitonic transistor when one can control whether the excitation, in which branch the excitation goes. Now, because these states are long-lived, one can reach thermal equilibrium and study the properties of the collective properties of quantum matters. So in particular, there has been a signature of exciton of Bose-Einstein condensation in an excitonic gas. So here you can see indirect exciton trapped And the quench of photoluminescence is taken as a signature of condensation of the excitons, because this condensate is is predicted to be dark. So this has been observed quite recently, and there's even like more detailed experiments, not just on photoluminescence, but also interference photoluminescence that can explore the many-body phase. So where we see the interference patterns in this kind of structures. Now, because these indirect excitons have a very small overlap, they also couple to photons very lightly. So what one can do is embed them in the microcavity in order to enhance the coupling to photons. And there has been a number of experiments that have been proposed of the application of a coupled quantum well in a microcavity. For example, application to quantum computing, and this is an example of a CNOT case that could be done with this kind of signals. It can also be used as a single photon emission. So that's coupled well in a cavity. Or there has been a proposition of doing like BEC of dipolariton. So starting with a polariton and going adiabatically to dipolariton BEC. So here I want to present how to study on the theoretical point of view this structure. And I want to give some analytical methods to find the energy and the lifetimes that give access to the spectra of this structure. So there are techniques that have been developed, mainly numerical, relying on the variational methods or exact resolution of Schrödinger equation. And here I show purely analytical methods. So I will go quite in the detail, and I've put lots of equations that will walk through like step by step to understand like our construction. So we are interested in a coupled well, and in different cases of figures. First, when there is no electric field, so this would be the conduction band or the valence band energy for the different semiconductors that form the coupled well. So in that case, one can form like what's called a hybrid polariton. Hybrid because it's the electrons are in the two well and the holes are in the two wells. So when there is no field, we have a hybrid excitons, and as we increase the field, this level here, where we have like the electrons starts to split, so that the electrons start being mainly localized in the lowest well and at the same time in the highest well. All the way, if we increase the field a lot, then we have this structure where we have both like the direct polaritons that would be in the same well, or we have this indirect polariton here. And we embed everything in a cavity. So the Hamiltonian of interest is that of the semiconductor, that's the coupled well, the photons, and the interaction between the two of them, right? So I'll start with the semiconductor, Hamiltonian, and electron hole.
May I have a question, please?
Yep.
For the F equals 0 case,
yep.
The electron, there is a small splitting between symmetric and antisymmetric wave function for the hole and for the electron. So you could have two kinds of or three kinds of excitons: symmetric, 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 antisymmetric, and antisymmetric, antisymmetric. Can you measure the energy differences between these ground states?
So we consider the symmetric and antisymmetric case in the case of these, like the high fields, because in...
But if you have a high field, the potential is not symmetric anymore. I specifically mean at F equals 0.
Right, so that is the dipolariton. So for this one, I'm not sure exactly how much would be if we can measure it. What we do is consider only one this kind of ground states carrier. Right?
Okay. So symmetric.
Right.
Okay. Thank you.
So this is like first the semiconductor Hamiltonian with electron hole and decoupling. So the one body part has the fields potential in it, and we split all the momentum. So we have like the z direction, and then we have like the plane that's perpendicular to it that's denoted with like these parallel indices. So we can split between the free motion and the one that's confined by the structure. And we denote like the electron operator with this A dagger and the hole with this B dagger. So that would be the corresponding wave function. For example, if we look at representation in space, then we have in the set, we have the confined wave function, which is schematically drawn like down, and we have the free motion in the plane that's perpendicular to the graph axis. Now, this one body part is diagonal in the carrier in the sense that here we have like everything that's the electronic part with the energies, and that's the contribution from the whole. So now we need to add like the interaction between the different carrier. So the expression in first quantization then can be given through second quantization procedure by this expression, where here we create from some electron and hole, we create other electron hole with some different momentum q parallel. And we can show that this interaction between the electron and hole actually only depends on this relative momentum that we write here. So what's important to notice here is that this interaction just depends on the overlap between the electron and hole wave function in the confined direction. Then if we look at think about this exciton state. So if the pair were 3, we would have just like the electron and the hole, but because of the interaction between the electron and the hole, we have correlated pair. So this B dagger is the operator that creates an excitons with a center of mass wave vector q parallel and a relative motion nu between the electron and the hole. So this operator is key here because that's the one that is diagonalizing our semiconductor Hamiltonian, right? So if we consider that we have only one pair, which is what we have in our system, we consider that we have only one pair, but I'll come back to this. Then, it can be diagonalized with these excitons and with their own energy, right? So this energy has the free energy of the particles and also some interaction through this that depends on the potential VEH. So with this, we have the semiconductor Hamiltonian. Let me now look at how would be the interaction with the photon. So we consider the photon to be created with the alpha dagger q. And again, we separate the momentum into the z direction and this q parallel direction. A photon interacting with a bulk exciton would be interacting with this kind of exciton having the same center of mass momentum as the photon. And with the interaction written here, right? So for annihilation of a photon, we have creation of an excitons. Now, because of the confinement in the cavity, then we will select this a mode of like the photons that we denote like omega naught. Now, the photons are not interacting with bulk excitons, but we have to take into account the coupled well structures. So again, what we do is split the momentum between the sets. So everything that was in the momentum here is now split between like the set and the parallel contribution. And we can show that the resulting interaction between the photon and the semiconductor is given by these excitons that we derived before, with some interaction here that depends on the overlap of the wave function between the electron and hole. So importantly, what needs to be noticed is that the interaction between photon and semiconductor here depends on this overlap of the electron and the hole. So if the excitons are direct and they are in the same well, then there is a very strong overlap and they are strongly coupled to the photon. If they are indirect, then they are in two different wells, but still there is a small, because of the leakage of the wave function for both carrier, there is a small and non-zero overlap between these wave functions, such that we do not need to invoke any tunneling. We can just take into account this overlap to have the interaction strength between the photon and the semiconductor. So that defines the semiconductor and the interactions with the photon. Everything what is left is to find like the cavity photon, and here just like a collection of modes. So if I summarize this on one slide, what is the system Hamiltonian that is relevant to the structure that we consider? So I will denote like two different cases. So the case where there is no field and we have this hybrid structure, and the case where there is high field. So in both cases, the cavity photons are not influenced, and it's a collection of harmonic oscillator. In the case where there is no field, we consider only the ground state excitons, so only the pairs that is on the level like that we denote zero for electrons being in the level 0 and the hole being in the level 0. And here we have only one pair that we consider. The coupling now depends on the strength of the coupling to photons with some correction due to the overlap of the hybrid excitons. And if we look at the general Hamiltonian, well, we would have to consider all the modes of the photon. So we just simplified the notation, and we have the general Hamiltonian with just like the cavity photon, the exciton that are the hybrid exciton, and the coupling here, right? So in that case, the relevant states are the polaritons, which are the exciton coupled to the photon. Now, what happens if we have like a large electric field? Well, the mechanism is basically the same, and I have not written all the details, but only the final results that we consider, which is the photons here. And now we have to consider that we have a sum of all carrier levels, right? They can be level 0 and 1 for the holes, and the same for the electrons. So one can create a photon that is coupled to two direct excitons, or so that would be or as well the photon coupled to one direct excitons. So in that case, we introduce the dipolaritons. So now I will show how we dealt with well, the spectra of this Hamiltonian, and what we wanted to do is to include the lifetimes of the carrier. So first we wanted to include the lifetime of like electron hole. So this was done phenomenologically in the sense that we transform all the energy of the electron holes into complex energy, with gamma being all the non-radiactive decays, right? It accounts for all non-radiactive phenomena. So it takes into account the coherence time of the excitons. And here we consider that the electron and the hole have the same mechanism leading to the coherence of like electron and hole wave function. So there's only this exciton inverse lifetime gamma x. For the cavity, we can do the same in the sense that we can transform the frequency into like a non-Hermitian frequency, and with gamma pH, like denoting, taking into account all effect of the cavity. So we end up with like a non-Hermitian Hamiltonian that we can diagonalize either, that we can characterize with like right eigenstate for H and then left eigenstate for H dagger. So this is what we'll do now. So looking at the right eigenstates, we know that it's a linear combination of the photon and the exciton. So that's a polariton. And one can just resolve the eigenstate problems to find exactly what should be the weights, this weights x, y. So we can define a branch that is mainly excitonic, in the sense that if we remove like the coupling to the cavity, we just end up with a pure exciton, and a branch that is mainly photonic, right? So if we remove the coupling, we have just the photon alpha. So these are the right eigenstates. Now we can do exactly the same with the left one that we denote Q. And what happens is that the quantities are quite similar here. What changes is that we have to take the complex conjugate value here. So once we have these eigenstates, then the time evolution is in principle given at all time, knowing, if we can diagonalize or write our initial state in this relevant basis and then get the eigenenergies. So let's have a look at the eigenenergies. And first, I look at a limiting case, in the sense that we consider that the lifetime between the photon and the exciton is the same, right? So how does the eigenenergy changes as a function of the coupling normalized over the detuning, so delta? If the lifetime is the same, then this coupling only influences the energy. So this energy here has been like shifted, but we would find, if we include like this shift here, we find like the photon energy and here the exciton energy. And it just increases linearly with the coupling. So the blue is the real part of the energy E prime, and the red are the imaginary parts. So here we have equal lifetime. Now, if we look, if we change the limiting case, and we now look as for different lifetime but same energy, so the detuning being 0, we can see that both the energies, so the real parts and the lifetime, the imaginary parts, depend on the coupling. For small coupling in these regions, the eigenvalues are purely imaginary, and all the way to the exceptional points, where then they become purely real. And here, the lifetime at large coupling is the average of the average value of the lifetime that we have chosen. So these are the limited case where we have either no detuning or same lifetime for the photon and the excitons. Now, if we look at a more general and maybe less idealistic case where we can have everything different from 0, so in that case, we take the detuning to be larger than the inverse of the difference in lifetime. So before we had, and now I'm plotting E prime and E and not E prime, so hence the shift. So before we had this case where only the energies were changed by the coupling and the lifetime was the same. So now we can say that both the energy and the lifetime are changed in a non-trivial way by the coupling. And if we look at the case where the difference between the inverse lifetime is larger than the coupling, so before we had something where we had like some exceptional points here, well, now if we do add the tuning, what we find is that there is no more exceptional points, and all the energies have their own like lifetime and eigenvalues at any point. There is no more coalescence. So this shows how for a given experimental parameters on this lifetime or the detuning, how the spectra will change and how it is broadened through the lifetimes. So this is the case for f equals 0, where we have the hybrid polariton. Let me now go for the case of large electric fields. And here I've written again like the Hamiltonian that is relevant, where we have like the photon with some lifetime here, and we have the direct exciton. So that would be the symmetric and the antisymmetric, the state that is dark, but these are like direct excitons, and we have some indirect excitons, right? They are higher level, but we only consider these three first levels. And what's interesting to note already at the level of the Hamiltonian is that the direct exciton here has an enhancement in the coupling of a factor of square root of 2. So if you look at the coupling of the indirect exciton and that of the direct one, then we have this factor of square root of 2 that comes and enhances the coupling to direct excitons, right? So these direct excitons are not just more coupled because of the overlap, but also because of this factor there. Right, so we can do the same as when there was no fields and look at the dipolariton eigenstates. It's again non-Hermitian Hamiltonian, so we'll start with the right eigenstates that I denote like P. So what happens is that now we have like the direct exciton, the photon, and in addition we have this indirect exciton. So we have this dipolariton eigenstate. Again, one can look at all the weights and find all the relevance factors, and we have these three branches, one being mainly composed of the indirect excitons, and one mainly being composed of the direct one, and one of the photons here. Now we can do exactly the same with the Q eigenstate. What's changing, I have not written the expression, but mainly these are the same as the P with just some like complex conjugates on the energies and of the excitons and photons.
Sorry, so, I have a question.
Yep.
Just maybe I missed this point. So in the previous Hamiltonian, are you considering a general coupling, or are you assuming like weak coupling condition to find these eigenstates?
There's no assumption of the coupling. It's
okay.
It's a pure diagonalization of.
Okay.
So yeah, you just get like a coupled system, 3x3 system, and then project on each of the states, and.
Okay.
And get this expression. Just that this here, the states are not normalized, right? We just decided to write it this way. Okay, it's actually more tricky to find like this energy. I'm coming there, but still we don't need to assume anything. So in that case where we have a field, then we could in principle find like the dynamics at any time if we can diagonalize, well, express the initial time in this right and left eigenvalue. So with the direct, indirect, and photonic branch. Now, what about these energies, right? So this energy we can also, well, solve for them. It's just like a third order equation that we can solve through, well, we've used like something called like Cardan's trick that allows you to solve like any third order polynomial and find the roots. So we also have like exact expression from this. So let's look at how these look like. Now we have two kinds of detuning, right? In the sense that we would have, if let's say this is like the indirect excitons energy, and then we have the photons, and then we have the direct ones. then, well, we need to define two decouplings, two detunings. So this would be like delta, and then this would be delta x. So how does this looks like, how the dependence of the eigenenergy as function of the coupling, direct coupling, looks like. So we take the case where the lifetime of the cavity photon is the same as the exciton, to have a look. First, so we have the branch that is mainly the direct exciton and just increases with the direct, with the coupling to direct excitons. The branch that's mainly photonic at the beginning decreases, and then there's some anti-crossing. So here we have maximum twice the coupling to the indirect excitons. And after these, then this branch is kind of left out because it is less coupled to the direct exciton. So we end up seeing like the branch most dependence on the indirect branch and the direct one. So this is the case for, so all the plane lines here are the energies, the real parts of the eigenenergies, and this dashed line here is the imaginary part. And in that case, we have chosen that the particle have the same lifetime, so there is no dependency, it's just a flat lifetime. Now, if we add like a difference of lifetime, so for the energy, we find some like kind of similar behavior, but what's interesting is to look at the lifetimes here. So the branch, we can start, for example, in these particular initial conditions that we have chosen. We start with at low coupling to the direct exciton. We start with a photonic branch being long-lived. And we end up with the one being the shortest lived if we increase the coupling. And what's interesting is that there is some coupling for which all of the lifetimes, all of the branches, so all of the state can have exactly the same lifetime. So in principle, one could tune the device to the region of interest. So here I show these two particular conditions where the direct exciton has a higher energy than the other two branches, and with these particular settings. But if you want like more detail, we worked out like more conditions in the paper, and yeah, you can as well use the exact expression. So let me summarize this. It's a bit of a loaded slide, but this is what we've seen. So we've seen how to derive the Hamiltonian in the coupled world for no field and with a field. So what changes is that with no field we only have these hybrid excitons, and with a field we have this direct and indirect excitons. So we go from hybrid polaritons to dipolaritons, and these are like the eigenstates that have been presented and allow to diagonalize the Hamiltonian. So to summarize this part, we show how like cavity photons couple to these excitons, like the direct and the indirect, in this structure that are coupled quantum well under some electric field. We built the Hamiltonian from scratch in order to derive the relevant states, and we saw that at low fields the photon couples to the hybrid excitons, while at large fields it couples to one indirect excitons and two direct excitons. And thanks to this like analytical formalism, we can see like the different branches and how the energy and the lifetime are affected by the carrier lifetime. So this closes my first part. If there's any question on this, maybe it's a good good point to just ask them now, because then I'll look at something different. And if the questions come later, then it's not a problem. So let me go to the second part, where we use non-Hermitian formalism to fasten the dynamics of open quantum systems. So this is a work that has been done in collaboration with Sahar Halipur, Adide Sakani, and Adolfo del Campo. And it extends the techniques of shortcut to adiabaticity to open systems. So let me start by setting the scene, because it's a different, well, this is applied for any kind of like structures. It's more about like control of the dynamics. So we want to apply some techniques for like open systems. And first, let me quickly review what is known like for isolated system and about a technique of control that is counter-diabatic driving. So imagine that you have a system that is driven and for which you can write and you know the instantaneous diagonalization of the Hamiltonian, right? So then it is known, you can write the adiabatic approximation that tells you how would the state look like if your dynamics would be adiabatic. So this was derived independently by Demer, Black, and Rice, and later on by Berry. So the question that we ask is that, is there a Hamiltonian that reproduces the adiabatic approximation, right? So we started with the H0 Hamiltonian, that for which we know the adiabatic trajectory. And the question that we ask is a bit reversed. Imagining that we know like the adiabatic state, can we build and can we find such a Hamiltonian? So the answer is yes, there is. So it's the original Hamiltonian with some correction. These corrections are the counter-diabatic driving. You can see the expression here. And what it does is basically kills all excitations to ensure that you have parallel transport. So everything at the end follows the adiabatic trajectory, even if you go faster than adiabatically. So this has been successfully implemented in the lab, started first with single particles, but then in more complex system in a BEC, where it's been used to reduce like the motion of the BEC. You can see here the controlled dynamic compared to the non-controlled one. And it's been used in a 1D quantum fluids, and we did implementation in a many-body system, a strongly interacting system, unitary Fermi gas, where we looked at the expansion and compression of the trap and designed like scheme for the control, right? So what happens during this trajectory is that...
Can I make a quick question?
Yeah.
So with this counter-adiabatic Hamiltonian, do you preserve populations that instantaneously or just at initial and final time?
Just at the beginning and at the end, exactly.
Okay.
So during the dynamic, you have to choose a reference dynamics, and you have to say during this finite time, I want to reach the solution as if I had gone like infinitely slowly. That means adiabatically, right? So what happens is that during the trajectory, you do like, you create excitation, you create actually more that you would have created, but you compensate for them at the end. So for example, if you want to like do a trap compression, you would compress it a bit more and then release it, right? And this counter-diabatic tells you exactly how you should do, such that at the end you have the right state. But during it, you can create many more like excitation than the reference scheme. So there's been a lot of success of this technique in the isolated space, where there is no interaction with the environment. And what we want to do is basically get rid of like this environment and go from isolated to open system. So there's been like former intents already in 2014 to do this in the group of Vlaco-Vedral, that was based on adiabatic, the notion of adiabaticity in Liouville superspace. So it was a bit well restricted to this framework, and a couple of years ago, there's been a number of researches looking at this problem for open system in specific cases, mainly the case of harmonic oscillator, and this was developed the group of like Ronnie Koslev and as well in Boston University, and we did some work with Adolfo Del Campo and PhD student Léonce Dupay. So what I want to show here is a general setup where general formalism, where you could control any open dynamics and create this scheme in a given time, right? So what we consider is a density matrix rho that is arbitrary. So for which we know, and this is key in the assumptions, for which we know the instant diagonalization, right? So because it is open, we have the eigenvalues that can be time dependent. So this is the trajectory, and this is the given in the problem. And now we say, what is the trajectory that will implement this state at all time t? So if you look at the master equation, just deriving it, you get very easily that you have a dissipator that depends on the variation, time variation of these eigenvalues here. And this, right, so this we found like two ways like to model it. So the first way is that is through a non-Hermitian system where this I gamma here would depend on the variation of the eigenvalues. So if you can have a system with some like gain and loss where the variation of the eigensystem enters through a non-Hermitian path, then well, you can show that you get the equation of motions that build the trajectory that you want. Now, this is actually not normalized in the sense that the trace, let me write it like this. So if we look at the variation of the trace, it depends on the variation of the eigenvalues. So we can build, instead of having just like a non-Hermitian Hamiltonian, we can impose like trace conservation, and this is what's been introduced by Brody and Grafé as balanced gain and loss. So the system has as much gain as it has losses. And in this case, we end up with a master equation that reproduces exactly the trajectory, but that is right, that has like this non-linearity, that has built-in non-linearity because this gamma already depends on the state itself. So this would be like option one, to implement the master equation that gives this arbitrary dynamics through balance gain and loss and the non-Hermitian system. And the second option is to look at it from a master equation point of view, where we have to build in this dissipator, right? So we can formally introduce some operator that, so some Lindblading here, so that depends on the eigenvalues of the trajectory. So if one could build this Lindblad operator with some rates that then depends on the time variation of the eigenvalues, then it's possible, at least formally, to write the master equation exactly as we want it, which is the one that reproduces the state. So while this is you see that this is a formalism that gives you, like for any arbitrary trajectory, give you either the non-Hermitian Hamiltonian or the Lindblad operators and rates. So note that this is in principle like non-Markovian because it's time dependent. So this general formalism, then you can ask, well, maybe it's a bit hard to implement because you need this instantaneous diagonalization of the trajectory, right? And this is also the same problem that was at the beginning of the shortcut to adiabaticity. And so in this example, we worked out like an example of how to apply these methods for the cooling of a harmonic oscillator. So you would start with some harmonic oscillator in a thermal state, and then at given temperature, and then we change we give the scheme to reach another thermal state, for example, fast cooling in a controlled time. So it's really looking at this shortcut, but from isolated to open system. So with this, I come to the conclusion. I just flash two take-home messages. So in the first part, we looked at the particular structure that was a coupled quantum well, for which I showed the physical states that are relevant and how the branches are affected by the carrier lifetime. And in the second part, focusing more on the control of open system, we show how general non-Hermitian Hamiltonian or a non-Markovian Lindblad master equation can be used to generate any arbitrary open trajectory. So with this, I'll just do last advertisements. We have some open positions as the group is growing. So if you are interested, you can drop me an email, or if you have further questions after this talk as well. And with this, I'm happy to close and listen to your questions.
Thank you very much. Any questions, comments?
I have a small question. So, can you hear me?
Yeah, go ahead, Federico. We hear you.
Yeah, I was wondering whether regarding the second part, this formalism is just for finite systems, or you have also generalization for continuous variables where the density matrix is infinite, let's say.
So for finite system, because of a finite rank, or you want continuous?
Yeah, because I was seeing that the sum runs up to R, so I was wondering whether it can be generalized to.
Yeah. So it's true. We assume that the rank is there, and we assume it's not dependent on time. When we worked out, so in this derivation for the non-Hermitian case, there's not a problem, because the rates are just given by these derivatives here. In the case of the Lindblad master equation, the problem is that we need at some point the rate here we need to divide by the rank. So
okay,
but we still worked it out for the harmonic oscillator that has infinite length. So I don't think it's limited, but the general formalism is, in the sense that we need this rank. We couldn't get rid of it, except in lift this restriction, except in this problem. So I don't think it's a fundamental restriction. It's something that, we didn't know how to remove.
Any more comments, questions? No. Everything was so clear, no questions. So, well, thank you very much again, Aurelia. Let's thank her again.
Well, and thank you for organizing this nice series. So let's see how it goes with the conference. Very good.